Alright, after we looked at some early analog integrated circuits from the early to mid 70s over the last month, today we're going to do something a little different. We're going to look at some early Logic ICs. And what we're going to look today is the FCJ111 JK flip-flop, manufactured by Philips, distributed among others by Mullard in the UK. And this is the actual chip. Here I have a tube of them. Mine is branded RCA, but RCA didn't originally sell these. Some of these FC series flip-flops and gates are actually copies of an earlier series by Fairchild. These are all diode transistor logic, so not the later TTL we're going to see, but also not the, I think, even earlier resistor transistor logic, but diode transistor logic. So let's get one of these out of here. They come in a relatively unspectacular dip package. This one is manufactured in 72, and I think this one was made by Philips. Well, I think they were all made by Philips, but these were actually sold by Philips and not branded Mullard. Or one of the other distributors. The part number here, the FC is the name of the series. The J tells you that it's a flip-flop. An H there would tell you that you have a gate, and a K tells you you've got a monostable or timer circuit. So we have a datasheet here, which is quite nice, and it's even in English. It's much better than the last couple of videos I filmed on these early integrated circuits, where most of the information was in a language that I couldn't read. So what is a little bit odd about these and the whole series is the supply voltage is 6 volts. It's not the 5 volt TTL level that we're going to get used to later. It's all 6 volts. The clock rate is up to 3 megahertz, which is, I think, quite fast for the 70s. Fan out capability 8. That's also quite reasonable. And then we have a nice picture of the chip here. Some descriptions of the logic. We're going to look at that a little later. What's actually interesting about this is that it is, and I think it says that here somewhere, it's a master-slave flip-flop. So it's a JK flip-flop. So it's a little more complicated internally than your standard JK flip-flop. If you look at this diagram here, this is from a datasheet by Valvo, who was the distributor for, I think, the German-speaking region, just like Mullard was in the UK. You can see this has quite a lot going on with it. And you see it's basically 2 flip-flops end-to-end. And a couple additional things. What is very interesting here is that we have a set input that is basically giving us the ability to control the output of the flip-flop independent of the actual clock. And we can see that, I think, a little better in the Mullard datasheet here. That gives us the pinout. Oh no, this is what we're looking for. So, direct set and reset action. If we use these terminals S2 or S1 and S2, we can directly control the outputs independent of the clock, which I think is for some applications quite useful. If we look at the truth table here. You can see this is mostly just a standard flip-flop. We can, if we put our triggering on the trigger terminal, which is the clock terminal, it's called trigger here. It's called clock in the other data sheet. They all vary a bit. You can see that if we just clock it normally, we get a normal flip-flopping operation. If we interconnect J and K, we get basically a toggle. And if we trigger on J and K, we get this. So I think that's all that we have to say about this datasheet. Right, here's just a quick look at the die photograph for this IC. The die is relatively large compared to the other ICs that we had seen earlier. It's about 4 millimeters by 3 millimeters, so it's a little larger in size. And you can also see, while this is still a fairly simple circuit, there's a lot more elements on this than on the other integrated circuits that we looked at before. Right, so after we had a little look at the die itself, let's see what we can do with this chip. And I think the first thing we should do is just explore the different pins and the basic functionality of this. So I have built a little circuit here that I think I'll place here. And what this has is it's a 555 that's set monostable, and I can trigger that here. This LED is going to light up if I do that. And then it also has two push buttons hooked up to S1 and S2. So we can see this direct clock independent setting and resetting. And also I have two LEDs, one on the output and one on the inverting output over here. So the J and K inputs are set up to float, and the datasheet tells you if you leave them floating, they will float high, and that is equivalent to actually pulling them up according to the datasheet. So there must be some, either by design or because they put some internal pull-up resistors there, these gates are internally pulled high. So first thing I'm going to do is I'm just going to press this button here, and we're going to get a clock pulse. And on the falling edge, it's going to toggle the flip-flop. There we go. And the set and reset inputs, if I set this, you get clock independent setting of the flip-flop, and if I push this, you get clock independent resetting of the flip-flop. There we go, it slipped out there. So set with this one and reset, set, reset. And then we can also just push this and get another setting. All right, so this isn't quite all that exciting, I think. But let's look what you could actually use this for. So I've got on this breadboard here two of these flip-flops connected to form a small 2-bit binary counter. I'll just hook up power here. So we've got the same arrangement. The 555 is giving us a clock pulse, and then we're going into the first flip-flop, and this has both of its the input J and the K input pulled high, and then we're going into the second flip-flop, which has J and K tied together and fed from the output of the first flip-flop. The clock is connected to each of these independently. So we have a synchronous flip-flop. So I'll just demonstrate that here. We put a clock pulse in. Now we've got this LED on the first bit, which is 1, 2, 3, and now we're going to roll over to 0 again. So we've got our 2-bit binary counter here. So you could imagine, from these gates you could build some control circuitry, some early computing circuitry. This all works fine. I mean, it's 6 volts, but besides that, you even get up to a couple megahertz in speed. This, I think, is pretty cool. And I'm, as I was on all of the videos, I'm quite surprised by the performance of these by now 50-year-old ICs. They work quite well. So I think for the next video we're going to have a look at one more of these DTL circuits, and we'll go from there. I hope you liked the video, and I also hope to see you on the next one.